I've got about 25 slides here, and Geo had contacted us to ask for some discussion about what we call the CERV, but a smart ventilation or demand control ventilation system designed for residences. And so I'll tell you, about half of these slides are related to air quality, but in a very abbreviated manner. On our website for Build Equinox, there's a lot more in-depth information on air quality. What air quality costs us, even though we may not have meters on ourselves like an electric meter, that there is a real cost to people getting sick, to people not being productive. And these are directly attributed to things like air quality and comfort. And so just a little bit about that. And then the second half talking more directly about this machine we call a CERV, but basically an automated way to take care of air quality and to ensure that we're living and working in a healthy environment. As I mentioned, I'm in central Illinois, and we like to tell people one of the advantages to living in the middle of nowhere is that we don't have any mountains or any oceans to get in the way, and so we tend to work hard while we're here. And then when we do have the opportunity to visit mountains and ocean, and that we appreciate them that much more. We're a small company. Ben is my son and my boss. And he fires me about every other day, and I still keep coming back. And then Alex is, the three of us are mechanical engineers, and in our background, we do a lot of R&D for heating, ventilating, air conditioning, refrigeration companies, from appliance scale, like refrigerators and dishwashers, to much larger. We, for example, are also co-owners of a company down in Florida that makes air conditioners for cooling commercial aircraft, the big boxes underneath the boarding bridges with the yellow ducts. Our company in Florida builds, these are 30-ton to 120-ton heat pump machines. And so we work on a wide scale and a wide number of applications. Overall, the thing, though, that drives us is that we are very mission-driven, that we feel that we need to live in a sustainable manner. The house I live in, that's also a test platform for us, but that we built in 2010. It's a zero-plus house. It provides all the energy, solar PV, an 8-kilowatt system for operating the house, plus enough energy for driving 2 electric cars, and has 1,000 kilowatt hours left over each year that we donate to the local utility. And so I think Aldo Leopold said it best, how do we live on a piece of land without spoiling it? But basically, how do we give future generations the same opportunities we've had, as well as around the world, that as we live more efficiently and more sustainably, that there's more than enough resources to go around to elevate the quality of life throughout the world. So from our viewpoint, as we looked around where we could contribute to living in a sustainable manner, we understand the energy in a very detailed manner. Where we saw the biggest need is in managing air quality, that we shouldn't just live in an acceptable indoor climate, we should live in an exceptional indoor air climate, and that there's going to be significant economic gains for us in many different ways because of that. And on our website, you'll find these 4: health, cognition, sleep quality, and productivity. And when you see those icons on our website, if you click on them, you'll see some good foundational papers. They're very readable, but they're peer-reviewed journal papers. One on cognition, the other one on productivity out of Harvard School of Public Health. the one on sleep quality out of the Danish Technical University, a leader in air quality research, and the one on health from Professor Donald Milton, who previously was at Harvard but is now at University of Maryland. And interestingly, just a week ago was on CBS News talking about how we catch the flu. And one of the reasons we catch the flu is poor air quality. As an aside, while we don't have this on our website, we do a lot of energy modeling. We don't try to do energy modeling as far as a business aspect, but my academic career at the University of Illinois was heavily involved in monitoring as well as simulating and analyzing high performance homes, high performance buildings. And out of that research, we developed this thing we call ZEROs, Zero Energy Residence Optimization Software. And I still go on campus and will teach in some sustainability and architecture and engineering classes. And typically it'll be a few lecture activity where the students learn to use zeros, and then they do a project, maybe designing an apartment in Boston or a house in Texas or anywhere in between, a house in Wuhan, China. And zeros allows them to do the economics and the financial analysis on homes. And so even though we're all about air quality, you can't get away from understanding how what you do on the one side, its relevance to the other side of things. And so if you're interested in zeros and doing some energy modeling, you can find it at this link. So even though you won't find that link on our website, and then it's free to use. We've got people all over the world using it, and you'll see some guidance into how to use it and some other things located on the website. And this is a very well-validated computational engine. My last doctoral student who informed me that I saved the best to last as far as graduate students, having about 70 advisees over the years. He's the one who wrote his PhD on this computational engine that we developed and then compared it with extensively. And so it is a very well validated model. So let's talk a bit about air quality. A couple of weeks ago, I went to the Better Buildings by Design conference and in Vermont. Great conference if you haven't been there, and if you have a chance to go, really a great progressive conference. Jacob Rakusin and Brian Just, Jacob who also teaches some with Yestermorrow, and Brian Just, who's an engineering manager with Efficiency Vermont. If you go to the conference website, you'll see some talks on material selection. And I thought they just did a great job as far as, how to select and what some of the choices are as far as low toxicity materials and materials that don't tend to off gas. Well, on that flight, I had a CO2 meter with me, and I found it was about 1,550 parts per million. And just knowing that, I knew my chances of getting sick were going way up, because the higher the CO2 level is in a building or in an airplane, tells me the fraction of air that I'm breathing that came out of someone's lungs. And from some of Professor Milton's work, you can predict the probability that so many hours in a room with such a level of CO2 that your probability of catching the cold or probability of catching the flu or the measles or whatever type of contagion, that is directly related to that level. But this level also tells me other things, like that if CO2 is that high, that the VOCs emitted by the humans in the room from their metabolism, that these are also quite high. It tends to indicate that particulate concentrations are high, as well as the biological concentrations. It's just saying we're not getting enough fresh air. And on top of it, these studies, recent studies by Harvard and Lawrence Berkeley Laboratory over the past 3-4 years, have indicated that my cognition productivity capability is decreased by at least 10% at what used to be considered a pretty benign level of CO2. And if you're thinking of someone in a work environment earning $50,000 to $100,000 a year, if they're impaired by 10%, that's a good 5-10 grand a year that it's costing that company, either extra employees or work that's not getting done, or poor decisions and poor quality of work. And so air quality really does hit us in the pocketbook. A little background about the CERV and our history. As I mentioned, we're an engineering R&D background is one hat that we wear. This is what the CERV looked like 10 years ago. And this is actually a picture from the presentation we gave at the North American Passive House Conference in Duluth. At that time in 2008, which I think this was the third one, there were about 40 people attending that conference. So if you've attended one since then, you've probably seen more people. But we were talking about the CERV then. And basically what's in here are the components of a heat pump, the heating coils and compressor and the cooling coils. And in this prototype fashion, we were just seeing if we could get this heat pump to work as an efficient energy exchanger. Well, as we moved along a couple of years in development, it evolved into this shape, which is what you'd see on our current website. And it became reality. And we had UL certification in 2012. Prior to that, we had a number of CERVs put in, about half a dozen in some local homes for testing. This is my house, what we call Equinox house. Here's the 8 kilowatt array. This also features rainwater harvesting, and you can see some things online about the house, but it is a 0+ house, has been from the day it was built and always will be. And these are a couple of solar decathlon homes that we've been in. And the original CERV that was installed in Equinox house is still in operation there, as well as the ones that are in these two homes. So we're hoping it has longevity, and we know at least at this point about 8 years or so. This initial CERV configuration, and we'll spend our time on the new model that's going into production in March. But basically, this is an air handler. It's got a couple of bidirectional dampers that give us the flexibility to operate in a number of modes, from recirculation to fresh air to free conditioning. And we'll talk more directly about those. And then this lower module, and these are about the size of like a dormitory refrigerator. This lower module is the heat pump, about 1/3 of a ton capacity, and really designed so that it manages the amount of energy exchange needed for proper fresh air ventilation. And at 1/3 of a ton capacity, the compressor is nominally about 500 watts, and then the fans, depending on the efficiency of the ductwork, will run anywhere from maybe 30 watts to 100, 150 watts, again, depending on the airflow and the pressure drop. The kind of homes that these have gone in, there's about 200 of them out there now over the past 4 to 5 years since they came on the market. We haven't pushed on the marketing side, and so we're basically word of mouth at this point, but coming out of our shell as we go into this new model that we're releasing. But we're in a number of homes, such as, this isn't the first passive house in Illinois, the designer of this home also designed the first certified passive house in Illinois, which has a CERV in it as well. But this more recent home, this is the first passive house in Denver, Colorado, first passive house in South Carolina, first passive house in Florida. And then this is a Vermont home, and we're in about 80 Vermont homes. And so that's been a very important development base for us. Vermont's a very good, challenging climate for us to cut our teeth and grow in. And And then these homes, which are quite small, say 1,000 square foot, but they build module homes from say 400 or 500 square feet up to 4,000 modular complexes, all using CERVs in them, and in a lot of situations, say mobile home park situations with rentals where the occupants' first interests are not anything to do with, say, energy or air quality, but other things. And so it's been a good place for us to learn about the different ways from homes like this where the occupants are very conscientious about the material selection and how they operate their home, to a number of the Vermont homes where that's not foremost in people's thoughts. But the key thing here, the key takeaway, is that energy efficiency and smart ventilation, you can have both. And smart ventilation actually helps you become more efficient. We'll talk about that some, but on our website is a very detailed report where we analyzed over a course of a couple of years, 13 Vermont homes. So daily data from the refrigerator, the microwave oven, the water heater, the mini split heat pump, the CERV, and everything else using power. And on average, these homes were using about 3,650 kilowatt hours per occupant, or about 9 kilowatt hours per square foot. And relative to FIAS, for those of you with passive house familiarity, this is about 20% lower than FIAS's new climate-specific goal on a per occupant level. And this 9 kilowatt hours per square foot of energy usage is about 20% lower than the German Passive House Institute target. And so we know homes with CERVs perform in very, very high energy efficiency levels. As far as say the philosophic strategy for ventilating a home, what's been prevalent to today is that people tend to think in terms of a low constant flow, one that meets ASHRAE 62.2 standards. And we don't believe, first, that the constant ventilation, or what we call one and done, is a healthy way to maintain a home's air quality. And then second of all, we feel ASHRAE 62.2 is low by about a factor of 2. That where nominally it might put you at about 10 to 20 cubic feet per minute of airflow per person, and passive house would nominally be somewhere in that range with their ventilation standard. We feel you need 40 CFM per person when it's occupied, and then of course you don't need that level of ventilation when there's no one there. And that's one of the key factors in demand control or smart ventilation, is that with the CERV sensing CO2 and VOC levels, knowing that you're exercising when you might be putting out 8 to 10 times more CO2 than you do when you're sleeping, that it knows how to modulate on that basis, or when there's 10 people versus 1 person in the home. This data, incidentally, is from a certified passive house with balanced ventilation going through an ERV. And this is about a 3-week period. When the couple was in the home, it was polluted. When they went away for about a week and a half, it wasn't. These levels, and these are readings that we took. These are field tests. They allowed us into the house to monitor air quality. This is where somebody was coming in to check the home periodically. And then they came back. And as soon as they came back, it was polluted again. And if you think of it, where ASHRAE 62.2 for, say, 1,500, 2,000 square foot home might have you ventilated about 50, 60 CFM, but now you divide it up around among 5 or 6 regions of the home, you might be getting just 10 CFM in the space, in any particular space, a living room, a bedroom, an office. And if you have 2 people there, you're getting less than 5 CFM per person, and you're just going to see the pollutants soar. And this is not what you want to live in. It's just not, it's not healthy. And so our strategy is that when we get above a threshold, we like to tell people that we think 850 is a good threshold to set on their CERV, that then it would bring the air quality back. This is real data from my house over the course of a year, 2017. And if you go to our website and on the menu bar, you'll see something that scrolls you down to a screen that says take control. This is a live control screen for my house. And you'll find that you can look at data from over 4 years. And then you can focus in on some of these other time periods, like this is around Christmas with family, and this green bar is indicating a heavy ventilation period. You don't see as much detail in this 1 year period. These regions are where my wife and I were traveling or out of the house for a period of days. And basically in our house, because of the material selection and the way it was designed, that we're the source of pollution. And when we're gone, the house is doing great. It basically doesn't need ventilation. Just a couple other slides, but again, on our website, you can find a number of newsletter articles plus other publications we put together. This is an interesting home that just started up around June of last year in New Jersey, and we worked with this group to design the home. And what's unusual about it is that usually a new house, even with conscientious material selection, goes through that new car phase, that new car smell, with quite a bit of VOCs being emitted, and usually a couple of months of high ventilation in order to keep VOCs contained, and then moving into a period where there's an interplay between CO2 levels and VOC levels. And this is typically what we want to see, is that a house, when it tends to be human dominated as far as the pollutants, and there's nothing much you can do about us if we're living and breathing, that, you know, we should be putting out CO2 and then the associated VOCs. That sometimes VOCs may dominate when you're cooking, other times CO2, but either one needs to be taken care of when it goes above whatever threshold. Now here's a house that was more conventionally built without much care taken as far as material selection. And so we don't really know the cause of it, but of course the homeowners were quite alarmed. They bought a CERV because they wanted to have excellent air quality, but it took almost from May, when the house first came online last year, to October to November to finally get to where this interplay is happening, where the human activity tends to be what's driving it. Instead of VOCs, whether sealants or paints or furnishings or other things selected, but it's good to avoid this, and for sure you can avoid this with good material selection on your parts. So a bit about the CERV. Yeah, there's a good time for questions.
The 850 parts per million, is that a standard that's been established by any particular body, or I mean, what determines?
No. Yes, and so the basis for that, with say ASHRAE 62.2 for residences, but then ASHRAE 62.1 for more commercial buildings, nominally that gets you to about 20 cubic feet per minute per person. And under what we consider sedentary, basically like the sitting at a desk doing office work conditions, that that you would, with 20 CFM per person and that level of metabolism, you'd have about 1,000 to 1,100 parts per million. And in the past, before we knew that CO2 in and of itself was really impairing our cognition, that seemed okay. And the basis for that historically was that it's the point where 20% of the populace is dissatisfied with air quality because of odor, not because of health, but because of odor. And so historically, and these were tests run in Harvard in the 1930s, they physically put a recently showered, clean clothed human in a box. They blew air through it at so many CFM, 5 CFM, 10 CFM, and then they had people on the other side of the box sniffing the air blowing out of another duct. And when they saw that only 20% were dissatisfied with the odor, that's when they decided that was reasonable ventilation. And while that's changed through the years, it's roughly come back to being that level of ventilation again. Now, this more recent work by Harvard especially showed that we have this cognition impairment that seems to happen down to levels that are, say, 600, 700, 800. But definitely by the time you hit 1,000 to 1,100 parts per million of CO2, that cognition is showing signs of impairment. And things like creativity, decision-making skills, focus, task work, about 9 different areas were tested for cognition performance in a number of test subjects. A follow-on work for Harvard showed, where they looked at the economics of that impaired cognition, showed that throughout the US, in conducting a number of building energy simulations and asking the question, okay, if we double ASHRAE 62.1 from 20 CFM to 40, what economic gain is there as far as personnel productivity and the value of that? And then what would be the energy costs without doing anything heroic like energy recovery in a variety of building climatic regions? And they found that from their modeling, and they did this with Carrier using Energy Plus, so very detailed simulations, they found that that the performance improvement of going from 20 to 40 should have an economic value of about $5,000 to $6,000 per employee per year, based on the Bureau of Labor Statistics salaries that they use. And they found that the cost per employee for that doubling of ventilation would be about $50 per person in the harshest of US climatic zones. So it's a very interesting, it's 100 to 1 payback, doubling that airflow rate in terms of cognition productivity. And let's say they're off by a factor of 10. Maybe it's only $500 instead of $5,000. But clearly, the importance for an employer for improving airflow exists. And on top of that, this other paper I mentioned off of our website that looked at doubling ventilation from current standards to 40. This was done by Milton, who specializes more in contagions and airborne illness. He found that sick days would be reduced by 1 to 2 days per year, which is about a $500 payback versus about a $40 to $50 per employee extra ventilation costs. And so these are the basis for the metrics that we've recommended to people. Of course, with the CERV, they can set their own standard on it. But we've been encouraging people to move it down. And so when you look at my house, for example, you'll see I have it set at 850. The reality is I'm much lower than that, and that's the upper threshold. When I get there, it comes back down. Right. That's kind of the history on that.
Right. That's very useful. Thank you. And the next question is it fair to say that some VOCs are more harmful than other VOCs?
For sure.
And if so, then is it possible that VOCs generated by poor material selection could be worse than those generated by people? Right?
You bet. You know, this is the complexity. So from the one viewpoint, because we encounter a number of people with real concern, and they're stressed out by, do I have formaldehyde, or do I have this issue or that issue? And on a detailed basis, it's such a complex soup of things, from what we put out to things that from cleansers and cosmetics to cooking that impact us. But here's, if you step back from the other side and say, well, we know what the solution is. It's more fresh air. If we bring in fresh filtered air and we bring it in enough, we know we're going to hit good, healthy levels. And hopefully we can help in whatever manner air quality impacts this growing prevalence of asthma and allergic sensitivities, as well as other issues related to poor air quality, particulates being linked to things like stroke and heart disease. And so we don't understand the origin or how all these things are, but we do know that if we put in enough fresh air, assuming the outside air is good, which is another concern, that should benefit us. But regarding your point about good VOCs, for sure there are. I mean, if you think of inhaled medicines, that's a VOC that's helping your lungs to open up and breathe. And in our latest newsletter, we have a little blurb about chicken noodle soup, that it's not just a placebo effect with grandma giving you chicken noodle soup that helps you feel better, although placebo effects are very, very important for putting you on a positive side of getting well. But that it definitely has things in it that seem to attack and soothe the respiratory linings of your respiratory system. So there's good VOCs for sure. There's bad ones, and then there's ones that each individually might not be so bad, like limonene, which is kind of that citrus smell and a cleaner, and it is not a good VOC at high enough levels. But ozone as well, if you take the two of those at concentrations that are at levels that are considered safe for each of those, and then you mix them together, you get a particulate that's like 2.5 micron that's deeply inhaled. That's not a good thing to inhale. So there's a lot of things to worry about, but at the same time, the solution really is just good management of fresh air into the house.
Right. Thank you.
Any other questions anyone would like to ask it?
I have a question.
Mm-hmm.
I have a question. So, is a CERV, I'm assuming not, but is a CERV sophisticated enough to where you got a big group of people in the main area and 3/4 of the house is empty? Is it focusing more on ventilating one area? The whole house just turns over at the same rate?
With the new one, and we'll see some of these options, but this new one we call the CERV 2, it has a number of, it's got dampering and zoning capability that will, what we're calling precision ventilation, but it will let you address, say, more concentrated areas of pollution as they occur within the house. The older model, and then this base unit without zoning, the strategy that we use in order to ensure good air quality when you have a group of people in an area is that we run at about 150 to up to 300 CFM, and which is still a low airflow rate compared to like a central furnace AC system. But at that level, when we hit the threshold, whatever pollutant threshold somebody has set, and we see that we need to bring fresh air in, at 150 to say up to 300 CFM, we can flush the house out quite fast and bring it down. And then the rest of the time, we're typically in one of the recirculation modes, and I'll describe those a bit later. But recirculation is important for a number of reasons, and this is where we differ from the low constant flow, is that we get the air quality of the house brought down. And then if you think of a house where, like our house is two old people shuffling around, and basically my wife and I are over here or we're over here, and 3/4 of the house hasn't seen a human for most of the day. But it's got all this stored fresh air in it. So when we're in recirculation, we're making good use of that fresh air that's in other parts of the house. The other thing is that particulates And about a year ago, I think January last year, is a newsletter article on particulates, but how recirculation is important for capturing particulates, and that in today's modern home, and especially today's high performance home, 90% of the particles within the house are indoor generated. Skin flakes, cooking particulates, abrasion of shoes and feet and things on the floors, that these are the source of the particulates as opposed to outdoor particulates. Today's sealed homes basically filter those things out. So overall, we have specifically designed it for those issues, and now with dampering, that we're able to address those regions with higher pollutant concentrations. And there's another gain in efficiency that occurs when the more concentrated you can remove a pollutant out of a home, the less fresh air you have to add in order to keep it at a high air quality level. So,
I'm in the Salt Lake City area, which is has pretty bad pollution, outdoor pollution.
yes, I used to live in Salt Lake. I'm a
You're aware of it then, okay.
I'm used to inversions, yes.
Yes, yes. Is there any, do these CERVs, can they do anything for that?
Well, the outdoor filter, so there's some filters that manage VOCs as well as have activated carbon or charcoal in them that help, but it would primarily be the filter issue on top of, but as far as some of the other issues related to the smog, the nitrogen oxides and that, when your outside air is bad, it's hard to have good inside air. And that's where, we have to just keep working to keep cleaning up the outside. And Carol, you were going to ask something else too?
Yes, so this is amazing. I just love this thing, but what percentage of desired heating and cooling do you lose with the ventilation part, not the recirculation part? And the second part is, so is the house less dusty because you're not, it's tight, but you're not sucking a lot of dust?
Oh, could you repeat the second one again on the dust?
This has to, I was reading about houses that are unbalanced, and your house will suck in air when you turn on the ventilation system through all the cracks and leaks. And that's why your house is dusty. So I would love to have a house that doesn't have dust in it, just because I'm lazy.
No.
Do tight houses with great ventilation recirculation system, are they indeed less dusty?
No, absolutely not, because you are a big source of dust. I'm sorry to have to inform you that, but we shed about a pound of skin a year. And of course, not all of it's airborne in that, but, and then there's particulates that come in on our feet, but then just the abrasion of surfaces and cooking. And so there's a lot of generation of particulates. And in that newsletter article I mentioned, from our analysis of how homes have been sealed over the years, somewhere around 1970 to 1980 was where we changed from about 50% of the particulates from outdoors to 50% of particulates or dust from indoor sources. And with hitting today's like 0.6 ACH at 50 Pascal type blower door, it's well above 90% of the particulates. As you seal up a home, one of the interesting things is that not only do you have less air infiltrating into the house with its particulates, but as those cracks get smaller, a smaller fraction of the particulates make it through those cracks into your home. In effect, your home becomes a filter. And so that newsletter article, though, has some detail as well as some references of sources for that information. Yeah, but I'm sorry to inform you, you're going to have dust.
To both Carol, actually, to Carol and Ron's point. So firstly, to Carol's point, if you're installing CERV on an existing home that isn't well insulated, then are you likely to lose more efficiency in terms of having to reheat cold air.
Yeah, you had the first part of your question, Carol. I'll see if I remember to come back to that. But as far as existing homes, and we've done a lot of research monitoring leaky homes. And I can't tell you the number of times people told me I live in a leaky home, my air quality is good. We go in and test it, and more than half of the homes have poor air quality. Because even in a so-called leaky home, and by leaky home with today's say conventional construction, we see blower door levels of maybe 6 to 10 ACH, where 100 years ago it was maybe 20 to 30. And as we've put in storm windows, we've sealed up rim joists and things like that, things that conventional contractors are normally doing. The places where the leaks used to occur around our rooms, the old house we used to live in, when the wind blew, you knew it because it was blowing through the floor joists and coming up through the floors. And so we really, our 1920s era home, it really was leaky with air flowing in. But today's homes, where the leaks are not where you live. The leaks are in the laundry room, and they're in the water heater room, or places where there's flue vents. And whether or not, as the air's moving through that pathway, you happen to get in the way of some of the fresh air moving through, from our field research, more than half the time you're not. That your bedroom is quite well sealed. Your family room is reasonably well sealed. And so we do see a need, even in conventional homes, with whatever level of an energy improvement it might have, that purposely moving air into every region of a house and then being able to monitor that and automatically manage air quality. Because the air quality we're talking about, trying to keep air quality, say, less than 800 ppm or lower, the human nose isn't good enough to smell that. You're not going to detect bad air quality. And so we need to rely on these sensors in order to automatically help us do that. But Carol, you had asked something about energy, and I've kind of forgotten that. If you could repeat that one, please.
So assume a nice tight house, and you're running a CERV. What percent of desired heat cooling are you using when it's ventilating? In other words, not recirculation, actually ventilating out.
So the CERV as a heat pump, and you can see these energy results in, there's a very detailed energy report we wrote for Efficiency Vermont about 2 years ago when we studied 13 of these Vermont homes in detail. But as the outdoor air gets cold for winter type conditions, our coefficient of performance drops at about 0 Fahrenheit. We're maybe at a COP of about 2. So you get 2 units of heat for each unit of electricity. We have no lower cold temperature operational limit. But of course, as we start getting down to -20, -30, we become an electric resistance heater. In effect, all the power, the 300, 400, 500 watts of power going in the compressor, that's coming out as heat into the house. And so when we're, say, above 0 Fahrenheit, say more 20, 30, 40 degree Fahrenheit range, heat-wise, we're putting out about 1,000 to 1,500 watts. And then doing that at COPs that will be, or heating seasonal performance factors that are around 8 to 10 or so. Now, when we're in ventilation mode, of course, we're bringing outside air up to as warm of a temperature as possible. If it's 30 out, we'll be bringing in 70, 80 degree air. If it's 0 out, we might be getting to 40 to 50. But if it's a reasonably, say, managed indoor environment, people are polluting in a fairly normal manner, say about 20% out of an hour we'll need fresh air, and the rest of the time we're in recirculation. What happens with the CERV when we're in this cold weather is we're bringing in air that's at about, say, 40, 50 degrees. And then the rest of the time we're in recirculation, and in recirculation we're running at, say, 80 to 90 degree delivery temperature. And so it's kind of a transient, if you think of it in that way, a transient energy recovery as well. We don't need and don't want any kind of preheater to the CERV as far as electric preheating. Frost that forms on our cooling coils during the winter is actually latent energy that we're converting into sensible. So as we freeze water on our cold coils, that's part of the heat that's coming out of the heating coils for either in recirculated air or fresh air ventilation. We're about 1/3 of a ton, and many of the homes, all of the Vermont homes are basically 1-ton mini splits. Used to be Mitsubishi was the main choice, but now Mitsubishi, Fujitsu, Hitachi, Daikin, Haier, they all have some excellent, very cold temperature. Now we're seeing down to -22 Fahrenheit with 100% nameplate capacity. They're inverter drive compressors, and in speed control compressors, they can efficiently move about 3 to 4 times their nameplate in an efficient manner. So like the 1-ton mini split in our house, it's cranking out at nameplate, but then as we get into spring and that starts slowing down, once it gets down to about 1/3 of its capacity, it's then more of on-off where it's not so efficient operation. But that's where the CERV is at its maximum, and the CERV is also an inverter drive or speed controlled compressor. And so the CERV then pretty well takes care of the heating and cooling load through that, say, swing season on either side of winter going into summer and then summer going into or going through the fall. So it's a pretty seamless operation on that. And it's running around 500, 600, 700 watts. So it's not a large load relative to other things going on in the house. But that report will dissect and detail that for you as well. Well, this is what the new CERV looks like. And it's about the size of a clothes dryer, and it basically installs like a clothes dryer. We've done a lot of things different between bringing the fans and the fresh air module and the heat pump into a unitized. So basically you drop it in place, plug it in, hook up the ducts, and you're done. We have an integrated touchscreen. It's our own, all the computer algorithms and control boards and control algorithms are our own design. So it's not third-party vendors supplying, say, a Johnson Controls or Honeywell Controls or something like that. There's only one place to point a finger when it's not working right. We see the need for fresh air increasing, and so where our older unit had 6-inch ducts, we've opened these up to 8-inch, and we've opened up the internal passageways where we had passageways as small as, say, 4x5 in the older CERV, and now these are 8 by 8-inch minimum passageways. And this increases our airflow capability as well as reduces internal pressure drop significantly. These are 2 ECM fans, one that's the supply fan to the house, and then one that's the exhaust. And there's a muffler section in here. And this is a damper section that decides whether fresh air or whether return air from the house is going to go through this coil and be recirculated back into the house, or whether fresh air from the outside is going to be moved over to this side for heating or cooling and then delivery to the house, with the other stream being moved to the other side. On the controls, these are very advanced controls. We like to tell people we had over-the-air upgrading before Tesla. And so the CERV never goes old. As we add new features and algorithms, we just broadcast that in a seamless manner, and you have new features involved. The filters, which used to be external, are ones that you can get in any big box store or online, 10 by 20, whatever MERV level that you would like. A number of folks will go to a higher MERV level during the pollen season or during the dustier summer, and then maybe drop down to a lower MERV level, depending on their sensitivities in the winter. These can be 1 inch or 2 inch, and they can be either standard filter size or Filtrete 3M size filters. So we've designed it so it can manage either of those, but nothing special there. If you want to use carbon impregnated filters, you can do that, but you don't have to go to a special source for the filters. And filters are very interesting as they go from being a benefit to being a hazard. They start being a breeding ground for bad stuff. And so regular filter maintenance is critical. Just another view of the CERV. So this is a touchscreen controller, but everything is online, and we just see more and more people wanting to work online. There's a few people who would prefer not having the wireless communication, and the CERV just in this form is fully wired, and so the wireless doesn't have to be utilized if someone desires not to. Basically, this is the return duct from the house and then fresh air. And then from that other schematic, the air drops down through the air handler region and either enters a duct moving underneath to be exhausted outside or to be sent inside. Because our maximum wattage is only about 750 watts, it doesn't have to have a dedicated circuit. It's a low enough amperage that it's not more than 2/3 of, say, a 15 amp receptacle, and so it can either have a dedicated or not. A condensate drain, we always have water coming out of the CERV, whether in the wintertime and through defrost, but again, that frosting to us is a benefit. We're squeezing some heat out of that. But then in the summertime, where under humid conditions, we will remove up to 10 or so liters per day. These two ducts are special ducts that, as we've learned in our initial 4 years, heat pump water heaters are more and more common. Every Vermont house has a heat pump water heater, and now every Vermont house has a heat pump clothes dryer. And these two ducts allow us to bring in, say, from, often the heat pump water heater will be right next to us in a small mechanical room, but some remote room. We can bring in the cool air from that heat pump water heater operation, and this lets us keep it separated from the main return so that it's not influencing our temperature and humidity readings of the air coming from the bulk of the house. And similarly, the heat pump clothes dryer, if you're not familiar with that, where a heat pump water heater will be cooling its surrounding space, and it's important to pull air through it to keep its efficiency up and to keep the space reasonably comfortable. The heat pump clothes dryer, a ventless clothes dryer, which is a big energy advantage for a home between not having to take a vent out and perforate a nicely sealed envelope, to also just being 2 to 3 times more efficient than a standard clothes dryer. But that room will get hot. That heat pump clothes dryer will run at about 750 watts. And in the typical laundry room, that will take that room up to being warmer. But the nice thing about this feature is that as we would draw air from a laundry room, and because we're always keeping air moving through it, humidity never builds up. And in the case of our house, my wife likes to use our laundry room as a drying closet. So she regularly pulls her clothes out halfway through the cycle and just hangs them up. And 8 years, no hints anywhere in the house of any mold, mildew, or any moisture difficulties. So we know that works, and it's a nice feature for the house. A little better schematic on the operation modes, and we won't go through those, but again, online, if you look at the control and operation of my house, with the historical data that you can also access, you can see when it's been in, say, ventilation heating versus recirculation heating. Free heating, which would be those Indian summer days when it's warm outside, warmer than inside, but the house is still at a point where it could use some heat. This ventilation set point and free cooling, but where no conditioning is needed, just bring air in the way it is, or just like when you feel you'd like to open up a window, the CERV is in effect automatically doing that for you. But at the same time, if you'd like to open a window, to go ahead and do that. That will knock your VOCs and CO2 down. The CERV will detect it and see that, hey, everything looks fine. And then just in the opposite manner, recirculation cooling, ventilation cooling, and then free cooling. Places like Colorado, probably 7 months out of the year, the last thing you want to do is go through a heat exchanger core and make the outside like the inside. You'd like to get rid of your inside air, just bring in that nice crisp air, whether it's happening 2 in the morning or you have a nice day full of it. This recirculation mixing, when no heating or cooling or pollutants are in their desired range, this is just the inside fan recirculating through the house. And this one's interesting because some of our early customers who really like the recirculation mode, and what's interesting is that because you typically are not hearing any operation or feeling a draft like you would with a large central air system, they could still sense that there had been air movement in various rooms of their home. And initially, when the CERV and everything was satisfied, the CERV just turned off. It just went into off mode, and then it would every now and then come alive and assess. And they said, you know, we'd still like to keep moving air around. And so we put in this algorithm and this mode and then broadcast that out to all the CERVs. So everybody has that feature. And I found that I like it a lot. And so when you look at the controls on my house, you'll see that 100% of the time when the CERV could be off, and that'll be happening more and more as we head into April and May in our region, that I just have air recirculating. And then this is an opportunity also to be picking up particulates, removing those. This just kind of shows a top view down of that fresh air and return duct. And then return air in recirculation cooling, it's moved through the damper system and through the duct. And the heat pump coil is a cooling coil in this case, and then it goes through the supply fan to the house. The fresh air that's going to be exhausted in recirculation mode, that goes through and picks up the heat that was put in the cooling coil. That's what's pumped over to this coil, and that's exhausted to the outside. Recirculation heating is exactly the same, except within the heat pump, we reverse this heat exchanger to be in a heating coil, and this one becomes a cooling coil. And then when we're in ventilation mode, fresh air instead comes over to the supply fan, and in the summertime, it'll be cooled and dehumidified. And this is another significant difference, is that we're typically delivering air that's comfortable, that exceeds comfort conditions. So cooler, less humid air in the summer, warmer air in the winter on average, as opposed to air that's not quite at comfort conditions. I mentioned a bit on the communications. In our current unit, there's a gateway that would get plugged into your router, and then we use Zigbee for local wireless, along with some N-Ocean. In this new model, we've incorporated the Wi-Fi gateway into our control board. And so there's no longer anything that needs to be plugged into a router. This will just find your router and will connect in. And then we liked N-Ocean a lot. As far as these local wireless, most people would think of Bluetooth, but Zigbee, XB, there's some other wireless protocols. And Ocean is growing in popularity in the US. I think actually its US headquarters is in Salt Lake City. But it's an ultra low power wireless, and that is ambient powered. So as far as like a wireless switch that is an option with the CERV. If you have that in your kitchen where you'd like to hit that switch to trigger the CERV into a immediate fresh air venting mode, it's your thumb energy that clicks a little piezoelectric generator that then allows the switch to chirp a wireless message over to the CERV to say, on the kitchen switch, I want you to run in fresh air mode at 100% fan speed for 15 minutes. But there's a whole range of other sensors, so a little photocell or ambient light powered temperature, humidity, and carbon dioxide sensors that people can distribute. And so as we move into more sophisticated homes where having zoning would be desirable, that these distributed sensors can be chirping their messages to the CERV, and they also act as repeaters for other sensors. That then, as we see that this zone should have more fresh air than that zone, this is a very nice way for us to build up the complexity of the ventilation system. At the same time, besides the wireless, we have wired inputs and outputs and expansion boards that let us more directly either sense that, say, a thermostat has been open or closed on a certain contact setting, or that we need to open or close a relay on a dehumidifier, on a geothermal heat pump, on various types of systems. And so we interact with the world outside of ourselves and in a number of ways. And really it's flexible enough so while it may be hard for someone to know whether we can do something or not, we can help you identify whether or not it could meet that application. These are some of the options, and I won't go through those in detail. I think I've got a couple of them here just to give you a few examples, but I mentioned these on Ocean switches, and then this is a remote temperature, humidity, CO2 sensor, a photocell that operates it. But somebody presses this switch, it's set up in the CERV to tell it I'm this fan in bathroom 1, bathroom 3, or the kitchen, and it will know what level of ventilation and for how long. Devices like these are wireless circuit transmitters, so instead of, say, a switch triggering a fresh air event, if one of these is put in a kitchen vent hood circuit or in the light switch going into the bathroom, when someone turns the light on in the bathroom, this chirps a message to the CERV that says someone's in the bathroom, go into fresh air mode. And then similarly, wireless relays so that we can power various things. And to give you an idea of that, this thing we call the Geo Boost, it in effect, if you put in a ground loop, and a number of the Vermont homes are now putting these in, but in the footer trench around a building, if you drop in a 1-inch plastic pipe and run about 1 GPM, this would typically be about 40 watts in like a Grundfos or Taco pump. This wireless relay can get a message from the CERV to kick on this pump to circulate fluid through this Geo Boost heat exchanger. And without any remote sensors in this, the CERV can determine then whether or not running this pump is a benefit. For example, in the winter, if we're bringing in cold air, we kick this pump on and we see that now the air warms up. We know that we were getting a benefit out of that heat exchanger. And it's very significant. When it's 0 or colder, this heat exchanger will take below 0 degree air and bring it up into the 30s to 40s. The difference between us and say some type of geo exchanger that you might see with an HRV or an ERV, those really have no energy advantage. They're really displacing an electric preheater, and they're just trying to get the air up to a temperature range that then that heat exchanger core can operate at without danger of freeze up. If you think about if you had the perfect HRV or ERV running at 100% energy exchange, if it didn't have a frost problem, if it was 0 outside and 70 in your house, 100% efficient energy exchanger would go from 0 to 70 and 70 to 0 without considering the moisture effects. When you put a heat exchanger like this in front of like an HRV or an ERV, now you're maybe going from 0 up to 32. And now as you go through the heat exchanger, you're going 32 to 70 and 70 down to 32. And so it hasn't added a benefit, but it's displaced an energy benefit, but it's displaced what you would have been doing as far as electrical with this pump. For the CERV, when we, instead of bringing 0 degree temperature air to the CERV, we're bringing 40 degree, we first see that additional energy that's been added to that, and the CERV's heat pump efficiency, its coefficient of performance increases. So we get both a capacity boost as well as an efficiency boost because of that. And so we're seeing this grow more in interest, and we've done a lot of testing here on that device just to ensure that when you drop a tube like that down in a footer trench, you're not freezing your footer, which is the whole idea behind having the footer below frost level. Typically, you're removing about 500 watts on a very cold day and distributed over 150 to 300 foot perimeter of a house. That's not a lot, and so the ground around it has more than enough to recover. This is a post heater that can be added to the CERV. So in the case of Vermont, with the minus 25 degree temperatures they got to experience this past January, they went back and added these to the Vermont homes. So this goes on the outlet of the CERV, and the CERV already has the controls for managing that. This was the first year after 4 years of the Vermont homes where they finally hit a temperature where the Mitsubishis started to drop out. They've had minus 15 to minus 20, and the Mitsubishis is kind of a fuzzy temperature line when they do drop out. But some of the homes that hit sustained temperatures of minus 20 to minus 25, the mini splits dropped out. Now the CERV's heating capacity dropped down to very low levels. It continued operating, but with a 3 kilowatt heater added to the CERV's outlet, this secondary thermostat control, as it would see that, hey, the house is now dropping below the main temperature set point. This shows 5 degrees below the main set point. So if the main temperature is 68, at 63, this heater would kick on. So they now have this as a backup, and it's been working great since they put that in January. So this is more on those vent switches, and then there's zone dampers, as we've already talked about. There's a lot of detail here for setting that up, but it is straightforward, and we work with folks as far as setting that up. But a lot of flexibility, and this is a simple example showing how with the base CERV without an expansion board, it has an auxiliary relay, and where we've seen more and more folks that would like to use the CERV for its local exhaust. So in ASHRAE 62.2, you've got the regular house ventilation, but then you have the local exhaust requirements for a kitchen and a bathroom. And with zone dampering, if you had returns, say, from all the bathrooms and laundry room, mud room coming from here, and then a line coming from the kitchen, if we don't have a damper in here and the CERV goes up to, say, maximum airflow, 100% fan speed, maybe 200 to 300 CFM depending on the ductwork. Well, this is all going to be boosted up along with this. And we've seen cases where then this isn't able to get up to, say, 100 CFM or whatever might be required for that local exhaust. By putting a damper over in this branch, and this could be right at the return to the CERV, this one could close off when the kitchen is either activated by the circuit sensor or a switch. Closes off so that the ventilation will emphasize the kitchen area and get that up to the local exhaust. And in many of the homes, like all of the Vermont homes, about 80 of those now, my house and then several of our other project homes, the kitchen hood is just a recirculating exhaust, not an outdoor exhaust. The CERV is the main exhaust for the house. And I can tell you from 8 years of fortunately having a spouse who loves to cook and doesn't realize our 4 kids have left the house, so it gets an immense amount of cooking of a lot of different types, that this really works. Wonderful cooking odors don't get infused and absorbed into your furnishings, so you don't get today's cooking tomorrow and the next day and the next. It just doesn't have a chance to get infused, and then things aren't getting greasy or that. You still want the recirculating hood so that the grease screens can catch those particulates, and that's especially important for the health of the cook, so that that's getting drawn away from them. But that capability is a very nice one, so that it doubles up the use of the CERV. Some of the things that are coming out later this year, with the previous CERV, we had this beacon we call server or CERV infrared. And the current model, we can control a Mitsubishi. This is my living room, and here's server. And basically it's just sending out the infrared codes for the Mitsubishi. But what that allows me to do as far as the CERV operation is that now I can control that Mitsubishi from my smartphone, from my computer, from other control interfaces. And so I can set that Mitsubishi, in my house I have 2. I have a 3/4 ton in one area and then this other one in the main living area. But I can distribute these beacons so I can control any number of the Mitsubishis with it. But the new one coming out, where this was a Zigbee-based communication, the new one is converted over to an Ocean. And then we're adding the codes for a number of other mini split units, Daikin, Haier, Fujitsu. And so somebody could have a mix of different mini splits distributed around their house and still be able to control it. It turns this into a smart unit because, for example, to dehumidify my house in the summer, these mini splits typically just have a manual mode, what they call dry mode. They don't have humidity sensors in them. So the CERV, when I need to get the house to, say, below 60%, 65% in the summer, I'll put it in dry mode for maybe an hour or 4 hours or whatever, and then take it out. With the CERV doing that control, and since the CERV has the humidity sensors, it can be moving this in and out of dry mode in the summer, or in the case of like the Northwest where you have cool wet, it makes it a modulating dehumidifier. So I can go into dry mode, get some moisture out, but then maybe put this into a heating mode. So I'm doing a modulated reheat. And so it makes it a more efficient way to psychrometrically move around within moisture and temperature space. There's some things online on what we are going to be building out in the future, but these things we call analytics that are built into the online, what we call service for the CERV. We're building up a CERV community, and this section is made of some metrics we've defined that tell you how well you're doing relative to ASHRAE ventilation standards. So if you're doing as well as, say, ASHRAE 62.1, 62.2, you'd be at 0. If you're getting close to fresh air, you're going to be improved. And if you're worse than ASHRAE, you're going to be negative. And these lines, which you can't read in here, but on the basis of health, which we relate to VOC levels and cognition to CO2, and sleep quality is really nighttime CO2, where CO2 can build up to undesirable levels that impair sleep quality. This shows how you're doing relative to the CERV community. And so it kind of lets you see how you're doing relative to everyone else with a CERV. But everyone else with a CERV, just from this data, is doing well also. This is a pollutant exposure. So as we integrate the number of hours we're in 1,000 ppm of CO2 or a certain level of VOC, we've defined in a manner similar to kilowatt hours a pollutant exposure. We don't know what to do with that yet, but we feel very strongly that as we accrue this, this is going to feed into future health benefits for me personally, as well as to others in the CERV community. And then here's some more basic statistics that if you start seeing VOCs outweigh CO2 by, say, a factor of 1.5 or more, that's telling you you've got something else adding VOCs rather than just your BO and showering habits. If CO2 will sometimes dominate in homes with gas cooking, often we'll see CO2 dominate. And then in all electric homes, if the human is the source of VOCs, CO2 will tend to dominate frequently because VOCs have other ways of disappearing as they get absorbed into furnishings and then later desorbed. But they also break down into water and carbon dioxide photochemically from sunlight, just from their bouncing around and reacting with other things. And so VOCs have other ways to disappear that CO2 doesn't. And finally, as far as the vision, we don't view ourselves as just simply a ventilator. Our goal really is how do we help ourselves feel better as best as we can every single day, and how can we contribute to us feeling better and what we're calling preventilation. And these days of big data and artificial intelligence, regardless of Elon Musk's paranoia about it, and rightfully so, any good thing can be used as a bad thing, but artificial intelligence allows us to take disparate sets of data from, you know, how many hours your TV was on to how many hours of sunlight and what the pollen report is, and then your CERV information and whether you exercise and the type of food you ate. And in some manner, things that impact our sense of well-being, a sinus attack, an asthma attack, an allergy attack, a migraine headache, a bout of depression, any and all of those and other things. Artificial intelligence is a manner in which things that are not so easy for the human to identify, that it can pick out patterns. And at some point in the future, we feel this is going to allow us to maybe mitigate or head off something that might end up in an asthma attack or an emergency room visit, or somehow help us avoid that altogether, or to identify those things that are, say, part of the factors impairing us. And so we're very excited about this future, and we feel, among other things, health costs are going to drop as things like this become more seamless and embedded and hopefully more helpful. And this last slide then, the future is now on a lot of these things. I don't know if you've seen this thing called Sense, but this is a screenshot for this electric circuit monitor. It's a very simple artificial intelligence powered electric energy monitor for your home. And what's nice about it, unlike the ones you may be more familiar with where you've got tons of spaghetti with all sorts of current donuts you put on all your different circuits, this has two current donuts that go on the main lines into your distribution box. And then through artificial intelligence, it starts identifying heat pumps and the solar and other things and whatever this heat is. But here, as it learned my house, it learned about the front right stovetop. and it's learned about the teapot and the coffee pot and the left fronts and the microwave. And so, and the garage door. But through this, when we see that somebody's cooking, instead of them needing to remember to turn on the vent fan, we see one of the appliances turn on, then we can tell the CERV, hey, there's activity in the kitchen, we should be fresh air ventilating now. This will also be coming up very soon as we develop skills, so that, hey Alexa, what's my air quality? Or Alexa, can you have the CERV ventilate for 20 minutes in the kitchen? This technology is here now, and we're excited about having a format that will let us integrate this in a manner that simplifies, hopefully doesn't confuse us. So I've talked way too much, as I told you I would. So I'll shut up now and be glad to answer any questions.
Yeah, I've got a few questions. Is that
You're back, Geo.
Yeah, I don't know what happened there. But,
I probably did something.
No. Can we use the CERV in a multi-unit building?
Yes.
How can it be used?
In a couple of ways with, and so the CERV is really people dependent. And so a small house with 4 people is really no different than a big house with 4 people, because really the source of the pollutants are the people, at least in a well-designed home with well-selected materials. There's some pollutants that are related to, the surface area, but if you're keeping away from those things like wall-to-wall carpeting and that, it should be people and people activities dominating. So let's say in the case of a duplex, with dampering. So the way the algorithms are set up and where you want to keep the air for duplex 1 and duplex 2 totally separate, you would have both supply and return dampers for each unit. And then each unit is designated a certain fraction of the CERV's time. If they're identical units, they'd each get 50% time. So half the time the CERV is looking at unit 1, the other half unit 2, but the 2 units can borrow time from each other. So if unit 1 is cooking and it's exceeding the threshold that's been set for that unit, if unit 2 is below its threshold, then unit 1 can be have fresh air brought in. And but if unit 2 starts hitting its threshold, then it's not going to sacrifice time for that allotment. But that's one manner. Going to more than 2 units, and it depends. If they're a single person like studios, maybe 3 or 4. But if it's 2 or 3 people might be in a unit, as you scale down, even though energy drops and the thickness of the walls don't have to be so thick, as you get into multifamily apartments, you've got maybe 1 exterior wall, maybe 2 if you're on a corner. The energy loads drop as you get to smaller and then say more multifamily, but the need for fresh air absolutely does not drop.
Right.
People dependent, and everybody, with cooking and that, you need to be able to handle that. And so you don't want to think, even though I know a lot of people think of, oh, I'm in a small apartment, now I just need an air exchanger this big and a tiny fan. It's just not true. It's going to be polluted and most likely smelly without sufficient ventilation.
So let's say, for example, you've got 6-plex. I'm just shooting a number around, just maybe because at its higher end.
Yeah.
On that situation, do you have 2 CERVs or 3 CERVs? How would you?
Yeah. I mean, we'd want to look at what the expected occupancy or occupancy capability would be, but. On the opposite side of that, we have some projects coming up that will be like 10 and 20,000 square foot homes, and they'll be 4 or 5 CERVs, and of course a house like that, money's no object, right? But in that case, the CERVs themselves will be organizing, and I mean, who needs 20,000 square foot home, half an acre? But they'll be communicating with each other so that they can interact and react to what's going on throughout that space. Because more than likely, it's probably still, you know, two old people shuffling around in one part of the house or another. So we can mix and match in different ways. Carol had asked about where you have a lot of activity and don't have activity, and we haven't had a project go yet, but we've had a couple of design exercises for like a yoga studio or like a brew pub, where a lot of time the occupancy would be quite low, and the CERV is able to manage, say, this 4,000 or 5,000 square foot space, but then you've got 60 people coming in. And in that case, what we've designed would be where the CERV is the brains and the main controls, but then a larger commercial scale type ERV, like a Renew Air, their 1,000, 2,000, 3,000 CFM series units that with an inverter drive on its fan drives at the CERV, but then just ramp that up to whatever's needed to maintain the air quality level that's been set. And then as that occupancy would drop, it would automatically lower that and then go back into full CERV control mode.
Okay. The other question I had is, I noticed that there's a horizontal CERV and a vertical CERV. Is that more to do with space orientation for space, or is it more to do with layout?
Layout. So that was the initial thinking with the design of the original CERV with the modules, was that with the fans separate and the filter boxes separate and the modules, that you could have a horizontal layout, which in the Solar Decathlon house, the one of the homes I showed, that was a horizontal layout in a loft. And in the other one, it was a vertical. But over the past 4 years, the answers come back loud and clear that the horizontal layout isn't a common one, much less than 10% or 5%. And that in those cases where that might have been, say, a preference, there's always been an ability to then have, you know, a space where this can be put in place. And the other thing, it's not as attractive as a washer or dryer, if those are even attractive. But, you know, this is going to go in a space that doesn't need to be, you know, viewed that frequently, but it needs to be a convenient space to change the filters, because you absolutely must make it easily accessible or people just won't change filters.
So how much estimation, how much space would you give someone who is putting in a CERV? I
mean, the Vermont are good examples where the smallest Vermont unit they built was a 600 square foot. And as precious as every square foot was in that, you know, they have a small mechanical closet with a CERV and a heat pump water heater, and now a battery pack shoved in there. So there's not a lot of space, but the nice thing with the CERV was that it could manage the cooling effect of the heat pump water heater, where, you know, the heat pump water heater manufacturers are definitely worried about people just putting it in the old closet where the water heater used to be without any air movement. But the CERV helps address that and manages that very well. But yeah, it takes up space that, you know, it's not space we're used to having to give up. But the value of fresh air, as we're seeing this wave of importance, you know, people's awareness is just growing rapidly, that they're seeing the value of making sure their design accounts for that space.
And the law does suggest that we need a 6x6, minimum 6x6, 6 feet by square, 6 feet for the CERV alone. Is that something that maybe building Equinox suggested, or is that something that they figure they've come up with all the work with that?
I would say, I mean, they have a very nice compact manifold system they've developed. And so I would say now this one has a smaller footprint than the current modular CERV with the manifolds on it, but it's maybe 6 inches in each direction bigger than this one. So where this is maybe 42, and so 6 inches more, maybe 4 to 5 feet. But then of course it's nice to have access on either side. That one's oriented more this way, where this one can be shoved into a corner of a wall and you don't need access to any of these back. The electrical wall switches around the front, condensate drains on the front, and then the electrical plug comes out the back. But it really doesn't need any clearance to a wall. So it will compact it more as far as that footprint.
Okay. Another question. In your opinion, when I was we were doing a house here in Vermont back in 2008, we had a discussion with Ashland, and they suggested they were actually preferring that the ERV or HOV was not connected to, let's say, if you had a ducted furnace like forced air.
Mm-hmm.
How do you feel about that? Is that a good thing to actually connect to the system, or is it better to have them separate?
In renovation retrofits, usually we can't get away from that because that's the way to get air in the other regions of the home. And so we would inject, in effect, fresh air into the return duct. And, typically in conventional homes with central air or central furnaces, that they're supplying return in every room. And so when that system is active, the CERV is adding that, and that's coming through the supply vents. When that system is off, the CERV then would go through both the return duct as well as the supply duct, but still end up going into those rooms. Now, the return back to the CERV for exhausting, that's really where the challenge is, to try to bring back air from, ideally from the bathrooms, laundry, and kitchen. And if we can get return air in some manner from those rooms, wherever fresh air has been put, it should work its way over toward those return spots. But what we want to make sure is avoided at all costs is that every space in the house should have air circulating through it in some manner. But generally, we've seen that that's not too bad to do in renovations with central air. If there are renovations with hydronic units in that, and then depending on if they're single or two-story or that, each one becomes its own challenge, just like retrofits do in general.
And I did have one more question, if you would allow me. How does the CERV, or does it even compare to, I think Panasonic had something out called the Intel vent or Intel balance? Is that even the same thing?
I'm not familiar with that. I'll have to look that up, and I'll send you a note back on that. I know Panasonic's been doing different things from their bathroom exhaust and their local ERVs, and but I'll take a look at that. We're always curious, and Panasonic was at Better Buildings in Burlington, but I didn't notice that there, but they might have had. They had a pretty extensive display, and they've been very aggressive on this front. And the companies are seeing that Healthy Homes is really picking up on their surveys, and so they're trying to figure out how they fit into it. And in today's era of high performance homes, the amount of heat that's needed or cooling in a house has dropped tremendously, but the capacity capabilities, as well as the ability to distribute it around the house to keep the house more uniformly comfortable, that's where the real challenge is. Now, the CERV helps even out that comfort, and with zoning, we'll be able to contribute even more. But when the sun rises on the east side of your house, it sets on the west side of your house, those windows on the east rooms are going to get warmer and need more air conditioning. And then in the afternoon, those west side rooms are going to need more. And that variation within these homes is where the challenge is to get more precision comfort.
Okay. The other question I'm sorry guys if I'm dominating this, but the other question I had was, oh, there was one more. On the kitchen. So I don't
Geo, I can't, I don't know if I'm the only one, but I can't hear you at all.
On the kitchen. Can you hear me now?
A little better.
Okay. On the kitchen. So I don't need to exhaust the hood fan to the outside. I can actually work it into the CERV.
Yes. So with the recirculate, it will pull the particulates and grease particulates through the grease screen. And in our case, then, we just throw those in the dishwasher periodically. They're stainless steel type screens. And then it just exhausts above it. And then we have two return vents to the CERV, a couple feet above that. But we do have a number of homes where, especially if there's gas cooking, I think you do want to exhaust that outside. One gas burner is equivalent to having about 6 people in your house. And typically you do want to have a fresh air source close to the stove if you have a significant range hood. Some of these range hoods are like, jet engines taking off. They're doing 1,000 CFM, and they're going to collapse the house if they don't, have something to bring in there at that rate.
Okay. All right, I do have one more question. Does anybody have another question? And that one more question is this: how would you handle if someone loves the CERV, you're going to put it into the home, and then they want to put in like a backup or a secondary heat?
Yeah.
And they decide to say, rather than going with a mini split, they actually want to go with, they go with the mini split. But then in case it gets like really, really cold, because Vermont gets down to like minus 29, minus 30 degrees.
Yeah.
So they decide to put in a gas, but it's something that they want to do. How can that be? Can that be handled in any way?
Now, so a lot of people have asked us, why don't we build up the capacity of the CERV so we can manage, the house load, where we've designed it toward really the ventilation load. And as we've learned time and time again, everybody wants the ability to do something different. So we're in homes with 3 mini splits, hydronic heating, and a wood stove. We're in homes with geothermal and then electric baseboard, and then we interact in whatever manner they would like us to. But we really, in many of these homes, we are the brains of the house and the main controller. So, for example, the Geo's neighborhood in Denver. If you look up Geo's neighborhood, you'll see what will eventually be about 250 homes. But they build out their first 6 units, and I think they've got 6 or 12 units under construction now. Those have small Bosch geothermal units, I think like a 2-ton unit, 1 to 2 ton unit, and then that's tied into the CERV. So the CERV is really the thermostat for operating the geothermal units. And then, as I mentioned, on the auxiliary heaters, like in Vermont, as they did experience the mini splits dropping out, they went in and added 3 kilowatt electric heaters that are on the exhaust of the CERV, and then those are tied into the CERV's controls. So when the CERV sees that secondary thermostat setting level hit, indicating that the primary, the mini split, isn't keeping it up at the upper temperature level, it kicks that in to bring it up. And in the case of these Vermont units, 3 kilowatts or 2 hair dryers worth of electric is more than enough to heat them. Actually, when I was there in mid-January, as they were installing those electric heaters, and I was working with them to interface them in the CERVs, these homes were like 80 degrees when it was 0 out with that just running full blast. And so, yeah, so, you know, but we can interface and, you know, radiant ceilings, we're seeing radiant floors where we're managing the zone controls on those. And so really it's just up to one's imagination, and then we'll help you figure out how it might interface.
It works. Okay. Great. Perfect.
Yeah.
Could these CERVs be installed in an attic or even possibly attached garage?
Yes, yeah, for sure an attached garage. We are in attached garages, and mine is in an attic space that's within the thermal envelope. And so it really is conditioned space, but it's up there. But so I pull down a stairway, but you know, I'm anal enough that I'm up there changing filters and stuff. And so that's the main concern, is just whether or not it's easily accessed for the filter replacement.
Okay. So even a garage would be okay. Attached.
For sure. Yeah.
I have a question too. So this relates when you were talking about the mini split and the remodel versus the versus new construction with the CERV. Where I am, mini splits are not that common at all. We have lots of heat pumps,
Yeah.
central heat, but not a lot of mini splits.
Yeah.
So the central air and heat already has the ducts.
Yeah.
But I'm assuming that the mini split must be more efficient heat pump than a regular heat pump. Otherwise, or I mean, is that the reason you use a mini split?
Well, it's mixed. First, in renovation, and you know, it really took off in Asia and then Europe, where with old masonry buildings, you just had to have a masonry bit and drill 2 small holes to run copper tube through instead of some kind of duct. And then you had nice localized conditioning. And that's true in the US in renovation, where, you know, just putting the outside unit on the other side of the wall for the space that you're adding or that wasn't being conditioned properly. But the other thing you said is also true. It is a highly efficient unit, and this era of what are called low temperature mini splits. And basically it hasn't been, there's never been a technical barrier to making a low temperature heat pump. You know, your refrigerator is a low temperature heat pump. It's operating at 0 Fahrenheit in the freezer to room temperature. It's been more of a demand for that market, and then to develop the components that could efficiently operate with enough capacity, so as it gets colder and colder and your house needs more and more capacity, that the drop in capacity of the heat pump was still sufficient to meet that house load capacity. And what's been done within the compressors that give it this lower temperature capability, if you think of what they call a recip compressor, but a piston cylinder compressor. There's a piston coming up, and you have a certain volume of gas, the refrigerant, you compress it, and then there's a practical limit where if you try compressing it more, you're going to smack into the cylinder. You need to have some tolerance. So you can only compress it this far, and the amount that you can compress it determines how much temperature change you can get in that refrigerant from, say, the cold to the higher temperature. So this new era of compressors have 2-stage compression. And so basically coming out of this first stage, the gas comes out and it'll go into a second compression chamber that can start again and now take it up that much more.
Okay.
And then with this era of speed control compressors, where they can run, say, up to where a typical motor running at 30 hertz AC or 60 hertz AC, these can run from, say, 30 hertz up to 120 hertz. So where their nominal rating at typical control levels for ARI, for the Refrigeration Institute, might be at 60 hertz. When it gets colder, they can start ramping that thing up toward 120 hertz to keep capacity going. But then as these energy ratings and Energy Star ratings require them to run a mix of, say, low capacity and higher capacity, they can also ramp down in speed where they're still efficient for that rating category and then get whatever overall CERV value. The mini splits, and especially the ductless, because the fan requires very little power compared to a ducted unit, they're seeing CERV values that are in the 30 to 35 range now, where just 10 years ago, the manufacturers we work with were crying when they're trying to reach a CERV 20. And then, of course, somebody broke the 20 barrier, and then everybody broke it within months of that, and then they started moving toward 30. And the mini splits have led the charge toward that. It's been interesting to watch. Now, I guarantee in Texas, you're going to be seeing a lot of mini splits because Daikin, the world's largest manufacturer of air conditioning and refrigeration, bought Goodman in Houston, and they're investing a ton of money there to show how you manufacture in the US efficiently. And that will be domestic produced mini splits coming out of there.
Okay. So definitely sound more efficient than a ducted.
Yes, yeah, but ducted, I mean, some people have their hang up over seeing the indoor unit, but then there's other reasons why ducted is nice for trying to distribute to other spaces instead of that one point source and then having something else like the CERV distribute it.
Well, that brought me to my next question. So with the CERV recirculating the air, having the mini split in one room, it still gets all the same cooled air and conditioned air in the other rooms, the recirculating CERV, even though the mini split is just emptying into one room?
Yeah, and if you think of it, if you have, say, with the CERV in recirculation, it's helping to even out comfort when you do have a point source or like 2 point sources, like in my house, the master bedroom area and the main, but then the CERV is moving that throughout as well as getting that unused fresh air back in.
So if it gets temperature changes from one room to another room.
Right, yeah, so it's evening that out. And with the zoning though, there'll be even more capability to do that as with these wireless transmitters that can be located. The temperature humidity that's a little solar cell powered, it's about the size of a doorbell button. And so you could stick, a dozen of those around the house. And in managing the dampers, our first priority is air quality, but when air quality looks good, to then work on evening out humidity or temperature as somebody would designate.
That's good. So the dampers are under the split is in one area. It could the air preference in a different area.
Yes. Okay. Yes. Yeah.
Perfect. Perfect. Okay, wait, that's not all. I did have another. Hold on a second. I lost my question. All right. There we go. Oh, and I think you said this, but I wanted to confirm. So the CERV can adjust the humidity even when the temperature is fine. Is that right?
We monitor humidity, but we haven't put in active algorithms for the CERV to control humidity.
So what happens if my house is a great temperature, but it's too humid inside? I mean, between the mini split and the CERV, what?
Okay, so so what I do in my home, and the reason for that is because the CERV's dehumidification capacity, while we're at about say 10 liters per day, a lot of Texas, you're going to see 40 to 80 liters per day in a well-sealed home, but with say reasonable occupancy. And so for us to use the CERV to control humidity, we've just found that if we're managing CO2 and VOCs, we're typically doing as good of a job with humidity as we can.
Okay.
But when humidity really needs to be managed, you need a bigger machine. So with this CERV IR beacon coming out, it will have algorithms that will allow whatever mini split brand to move into its dry mode or dehumidification mode, and then the server can take it back out of that mode.
So the mini split itself can do just humidity without temperature change.
That's where you get the bulk, yes. And you've got to look very carefully at the mini split specifications. The Daikin has some of the highest latent capacity, I think up to about, and I can't remember if I'm getting pints and liters mixed up, but liters about twice a pint. But it has about 70, maybe liters per day, but if not, it's pints per day, where like a Mitsubishi and others in their dehum mode are about 50.
Okay.
And so, that Gulf Coast and the Daikin is a good selection there. They haven't had the cold temperature range, but now their newer models are dropping down in that level too.
Okay, great. And my last question was the slide that you have up about the AI power monitor. What did you say the name of that was? Sense?
Oh, Sense, S-E-N-S-E. Yeah, if you type Sense, it will kick up, but it's a little orange box. It costs like $250. And it's folks from MIT, from what I've read, were also part of the development team for Siri. And so, of course, they want to control everything in your house, and this is their initial inroad into it. But I've just found it a very interesting device, and then very easy to, you tie it into the 2 voltage lines, and then you have 2 donuts that go on the mains. And then you kind of help it along. So as it saw the teapot, it didn't know it was a teapot, but it saw that there's some electric resistance heater. And then I just would notice that, whenever the teapot's on, I saw, heat 3 or something kick up.
Okay.
Then I just renamed it as teapot. And the same for the front right stove or the oven. It gives you this very fine-grained look at things that, would be more sub-circuit level. And then, so for example, now my wife isn't really thrilled about it, but I can tell her, you've made tea 82 times this month. And so it's, so it's quite interesting. Or the garage door opened 95 times, so far this month. It's kind of interesting look at, how a house operates.
Yeah, no, it looked really cool.
Yeah, it is. Yeah, and it's worked great. It's a real-time energy monitor, and so it's really nice, fine-grained wattage is showing up on it too.
Yeah, that's good. Actually, I don't know if this isn't really a CERV question, but talking about the heat pump hot water heater, which I just read about last week, and sounds great. But then, as far as the tankless water heater, is the heat pump one more efficient? Because you still have to keep the water hot all the time in the heat pump tank versus the tankless.
And actually, we have an article in our latest newsletter that has a small article on heat pump water heaters in comparison with, say, electric tank and an instantaneous and gas. And but the thing with instantaneous, so let's say electric instantaneous versus electric tank. Mm-hmm. Electric tank has a tank of hot water sitting there. But of course you can super insulate that so its losses are less, but just with a good, well insulated electric tank water heater and with typical usage, say daily usage, and daily usage is about 18 gallons of hot water per person per day. you would see about 5% improvement having the tankless because it doesn't have, say, as much standby loss as the tank heater. So it's not a large energy benefit.
Okay.
So the electric cost is really just about the same, and there's a pretty broad range of costs for the tankless. But where looking toward the future and electric rates, I think we will be moving more and more into demand charge as well as time of day rates. It's unclear what that will be, but what are common right now in industrial and commercial settings, where if you use 10 kilowatts for 15 minutes, even though the rest of the time you're only using 100 watts, but you use 10,000 watts for 15 minutes, if they have a demand charge, and $8 per kilowatt would be a typical demand charge. They multiply 8 times that 10 kilowatts, you're going to get an $80 charge for drawing electricity at that rate, at that power. And also that normally ratchets around so that once you hit a 15-minute window of a certain draw, now you're going to get that $80 charge for a year. And once you ratchet around for a year, then it'll drop down to whatever your next draw was for a year. And so it's a pretty significant detriment if that starts coming in place, where a tank water heater, so now with time of day, where at nighttime, low rates, early morning, afternoon, everybody's getting home, or a sunny, hot afternoon, the rates are sky high because of the usage. With a tank water heater, you can make your hot water at night and then use it during the day. And with time of day, you actually sometimes see a negative electric rate where the utility doesn't want to shut down a plant. And so they're begging people to use electricity rather than shining it into the ground. So they'll actually pay you to use it in some manner. But the tankless doesn't give you that flexibility to shift or have that thermal storage capability. So the heat pump water heater, typical prices now are about $1,000 a water heater. I know the Vermont people with the volumes they're buying now are getting them for like $700 a water heater. But let's say $1,000 versus $500, which I used in that article. But then you're getting almost a 3-to-1 advantage of, for every unit of electricity, you're getting 3 units of heat. 2 of the units of heat come from your house. The other is the unit of electricity you put in the compressor to drive that heat pump. But the payback on that with typical electric rates is quite short, and over the lifetime of the water heater, it's significantly less cost per month. And in Texas, the other advantage is that the conditioning for most of your year, both the dehumidification and the cooling, is an advantage.
Yes, that's true. That's true. Anytime we can pull heat out of the house, that's a good thing.
Yeah, and it's doing both heat and moisture. And it turns out that 18 gallons of hot water a day, the energy it takes to take 50-degree water up to 120 degrees, averages out to be about 80 watts. That a heat pump water heater would be pulling about 80 watts or so of heat out of your house to put into your hot water. Your metabolism is roughly, except after listening to my kind of monotone voice for more than an hour, it's about 100 watts. And so you can really think of it as, in Texas, your metabolism is getting drawn in by the heat pump water heater to heat your water, and then it goes down the drain and out of your house. So
that's pretty good. So I have had one negative thing about the hot water heater versus electric. It said the capacity is 12 to 20 gallons per hour, which seems really low if you're having 2 people take showers back to back or you have company over.
If you have teenagers, you'll find that to be an advantage because there's not enough hot water in the world for teenagers. And so having the tank run out of hot water is a good thing. And the same for encouraging visitors to not stay too long. But, that's, adding an extra tank and they'll be increasing that. But, slow water heating is actually efficient water heating. And the lifetime of these, even though some of the early ones like the GeoSpring from GE and that have had a few hiccups, the thing that goes wrong with electric resistance heaters is that electric resistance element. In a water heater, it scales up. In a clothes dryer, it corrodes. And in a refrigerator, it's the defrost heater, the electric heater that goes bad. They're just really stressed. Where heat pumps, the reason you change your refrigerator usually is that you don't like that color anymore. Nobody's buying avocado. So, but yeah, properly designed heat pumps should last a long time. And then they've been putting crappy fans in them. They'll be getting quieter and quieter as they put in more efficient, less noisy fans.
Okay. Okay, thank you.
You bet.
My questions, sorry.
Well, Ty, you've been so generous with your time. We have to thank you. It was amazing, amazing presentation, a lot of good information. And I'm sure if we have more questions, we definitely will be not calling you.
Forward any questions anytime, but we appreciate the opportunity to, just tell people what we're about and our activities and check over a lot of that information and ask us any questions anytime.
Oh, no problem. Thank you. Thank you very much. And just to show our gratitude here at Yestermorrow, what size T-shirt do you wear?
Like a large.
A large, all right.
I'm trying not to get larger than a large, but a large.
I'll do that. Yes.
Yeah, appreciate that. Well, good night, everybody. Thank you very much for participating.
Thank you.
Thank you. Very well. Very well done. Thank you.
So everybody else, you guys, if you have any, it's after 9, so I'm sure you are pretty tired, but if you got any questions regarding your assignments, shoot. Or we could do it at another day if you guys are tired out.
I'm really tired.
Yeah, I am too.
Okay. Grace, did you get that link for the video?
Yeah, I watched the video. It was nice to hear kind of all the troubleshooting that everybody was doing. Yeah, interesting hearing about Carol's design problems and things like that, or challenges. But I called PBS, and it sounds like they have an open house on April 7th, which is kind of a ways from now, but I'll make it up then, if not before, if I can figure out some way to go up during the week before then, but we'll see.
Okay. I know Vermont, they're very open to, if you want to go in and check out their place, they're open to that. I mean, they're not far from PBS. They're just north on 91.
Yeah,
so,
yeah. I definitely, if I go to one, I'll try and go to both.
Okay. And I'll see if there might be another one close to you. I'll can't remember where it is. I'll have to ask John, but I'll see. I'll send you that. Okay.
Okay.
Everything's going on. How's your plans, your design going?
I haven't done much work. I definitely need to do a little bit cleaning up, just in terms of saving groups the right way and stuff.
Good.
But before I move on, but I have a little bit more to do.
Okay, great. All right. Carol, we'll talk to you sometime tomorrow.
Actually, we're leaving town at 6 a.m. The road. We're going to out-of-town wedding. So on Monday, how about Monday?
Monday's perfect. Monday's perfect. Okay.
I'll email you when we're back.
All right. And Ron, how are you doing? I can't hear.
I made a lot of progress. That session with you was very good. So it's looking good. It's looking good.
Okay.
No question.
Just drop me a note if you need any help.
I will. I
Okay,
will.
cool.
That was very helpful.
I checked out Irontown.
Thank you.
It looks so fantastic, but they will not come to Texas.
Oh, is that right? Oh.
I was so sad. Like, this is great.
They did look pretty nice to me too. I wasn't sure about Texas, but it's good you tried.
Good.
Yeah, they said no.
Joseph, did you bring the donuts? Did you bring the donuts, Joseph?
Can you hear me?
I can.
I did have a question about air quality. I have a forced air system. You know, and I've never really given much consideration to air quality in the house, and I didn't realize there were so many things that came into play. With my forced air heating and cooling, is there something I can do today that might improve my air quality? Not that I know that it's bad, but you threw a filter or something?
Well, see, the thing is, the system you have is what is it? It's a ducted system? Is it the heating
Correct.
and the air conditioning you have? Is it a ducted system? Okay, so
Yes.
right, and so that only works like, you know, when it's hot, you're going to turn on the air conditioner, and when it's cold, you're going to turn on the furnace. Whereas with the CERV, with the ERV, HRV, whatever you want to call it, what ends up happening is that in this case, it actually moderates the type of air in the home and in different zones in the home, and it will send the correct amount of air, as Ty was saying, to that part of the home that needs it. I think, you know, the only way to do it in an inexpensive manner is to, you know, put a like a fan that that'll run through your duct, and you know, and you've got to set that at a, you'd have to set that up. And I think if you're going to do all that, you probably should look at something like the CERV to help with that. I mean, if you heard Ty, what he was saying is that they do a lot of work with retrofits, and so a lot of times they'll go in and they'll connect to the furnace or the air conditioning ducting system.
How much did the CERV cost?
Good question. How come no one asked that question? I think between 1,400 maybe 1,500.
That's not bad.
maybe even a little more. And I'm talking American dollars too, not Canadian. So anyway, yeah, maybe that's a question I can send you. Go ahead.
I also thought it was interesting when he was saying something about sleeping. It made me think that my teenagers sleep with their door closed. Like the boys are in the room, and when my daughter has sleepovers, she could put 3 or 4 girls in there, and they sleep with the door closed. And it just made me wonder if they're creating a CO2 concentration in there overnight that may not be healthy for them.
That's very well possible. It all depends on how tight your house is. If your house is really tight, you gotta, yeah, that's what's going to happen. That room is going to fill up with CO2 over the course of the night. I mean, I'm sure you've got a return air grill, and you've got, you know, they may have the window open. I don't know, maybe now if they have the window open, but they may have the window open. You know, if the house is a leaky house, I mean, there's still CO2 accumulating, but I mean, over the course of the night, it will seep out.
Maybe that's why they act so goofy in the morning.
That's probably, well, there you go.
Geo, basic question, but is the CERV connected, ducted to each room separately? And how is that ducting different from just a conventional ducting system? You might have covered that.
The way they use it at Vermont is that the first few feet are, I believe, are actually no, they use traditional duct.
Oh, they do.
It's just a traditional metal duct that they duct to each part of the house.
But there's an individual run to each individual room?
No, you get a main branch, and then from the main branch, it branches off.
But how does it know to go to like the kitchen versus the bathroom?
Well, I mean, what you do is you get somebody, you get someone to design the layout for you. I mean, so what you do is what you're picturing. The CERV, you've got an outlet for supply, you've got an outlet for return, there's an outlet for There are another two outlets, which now I can't remember. Supply, return. Oh, great. Anyway, so the supply is the main duct that's going to run, let's say, into a central part of the area and then branch off to, let's say, all the other rooms. Okay, and then in the rooms you're going to have a duct which is going to run back to the return,
Right.
for the air. So I mean, that's the idea of how they do that.
But I thought he was talking about, the bathroom specifically needs, venting for 5 minutes.
Yeah, the bathroom they would attach that to, yeah, then you have the supply, the return, and the exhaust, or the air going out. So that what it does is it's a fan. It sucks the stale air out of the bathroom, or the moisture out of the bathroom, and then it runs it through the CERV, and it exhausts it out into to the outside after it does its changing of.
But that would be through the whole. That would be through the whole house. It wouldn't be specific to the bathroom then.
No, it would be wherever there's stale air. So the more you get stale air and moisture in the kitchen, more in the kitchen, the bathrooms, and there are areas of the house where, if you remember, I believe you mentioned that there are areas of the house where, it's supplying air, but if there's nobody there, it just recirculates the air. There's no real supply.
All right. Okay.
And now they have baffles in the ducts. Or
Yes, they have the what do they call them? Dampers.
Close the duct or open the duct. So I did forget a question, because he mentioned the dryer is recirculating, the vents recirculating. No, those are not vented to the outside, correct? Isn't that what he meant? There's not like a duct going through your skin from your right. So that's the same thing for the bathroom. There's no vent from the bathroom going through your. It's just getting recirculated, so it's keeping the envelope closed.
Well, the envelope is closed. So what you want to do is you don't really want to puncture the envelope.
Yeah.
In more than one place. So the exhaust from the CERV is your out, and the intake from the CERV is your in. And so any moisture or stale air is coming from these areas, like the bathroom and the kitchen, and is being extracted. I mean, it's being used and then being extracted out.
Yeah. I didn't think I realized that's amazing.
Yeah, because when he mentioned that about the hood fan, because the hood fan has always been exhausted directly to the outside. Yeah. But now it's like, well, you can connect it to the CERV and it'll exhaust it from there. And not only that, but now you can use the hood fan to supply air,
right,
as well, when it's not being used, which makes sense, which makes total sense. So
yeah.
All right. Anyway, thank you everybody for showing up, and we will see. So these next 2 weeks are work weeks. So if you need any help with anything, please call me or drop me a line or email, and we'll set something up. Okay.
Thank you, Geo. Thank you for getting that speaker too. He was really.
No problem. No problem.
Thank you.
You're welcome. You're welcome. Have a good night, guys.
Good night.
Bye-bye.
How do I do that? Like that. I guess you will be receiving